Alright, so let's work here several problems within the video, and hopefully we can get through most of all these. The first two are pretty easy, the last one takes a while. 1027, 1028, 1032, okay? 1027 is a pretty simple, straightforward question, but I wanted to consider it because it's really important that we understand this, okay? 1027 asks us, if you have a molecule or an ion's formula, what is the first step to predict the shape of that molecule or ion? Okay, and the thing that I want to impress upon you here before we start talking too much about shapes of molecules, etc., right, is that the first step to figuring out the molecular shape is to draw the Lewis dot structure. You have to be able to do that. Crucial skill for figuring out the molecule shape. If you can't write the Lewis dot structure, you're not going to be able to figure out the shape of the molecule. You'll just have to guess or something at the problem. So really crucial skill. So if you haven't mastered that, go ahead and practice it. Okay, it's very, very important because what we're going to do is based upon the Lewis dot structure, how many bonding pairs, how many lone pairs are present around each central atom. We're going to invoke what's called the Vesper theory, Vsepr. And it's a pretty simple theory. It just says that the electron pairs are going to get as far away from one another in space as humanly possible. And to figure out what shape that results, we need to know how many electron pairs are present, which means we need to be able to draw our Lewis dot structure. Okay? 1028. When is a molecular shape, the shape of a molecule, identical to the electron group geometry? Okay? So I want to spend a minute making sure you understand the difference between these two terms. Molecular shape or molecular geometry considers the arrangement of atoms. Molecular geometry considers the arrangement of the atoms. Where are the atoms placed relative to one another, and what shape results in the molecule? The electron group geometry, or the E group geometry, shorthand. Okay, so when I say E group geometry, I'm talking about the electron group geometry. The electron group geometry describes placement of electron pairs around the central atom. It considers all of the electron pairs, whether they're bonding pairs, bonds, shared electrons, or lone pairs. Doesn't matter if they're lone pairs or bonding pairs, it considers them all. Okay? So these two things can be the same, but they're also sometimes different. So when is the molecular shape identical to the electron group geometry? That case results when all of the electron groups are bonding pairs. In other words, around our central atom, there are 0 lone pair electrons. There are no lone pair electrons. When that happens, the special condition of molecular shape being equivalent to electron group geometry occurs. Okay? And hopefully as we get into this Vesper thing, you'll get a better handle on this, okay? Because it's something that is important to understand this terminology, this vocabulary, because it's really easy to ask questions. Oh, what is the electron group geometry around the central atom? What is the molecular geometry? And you have to be able to read that term and interpret what that means to get the question correct, okay? Now in 1032, what they're asking us to do is to provide a sketch of different molecular geometry. There's no sketch of different molecular geometries. What these guys actually look like in three-dimensional space. Okay, so I'm going to see if I can quickly find some parts I need. I've got these little model kits that I'm going to show you here. This one seems like it'll work. Oops, no, that's tetrahedral. That's not going to work. Where did my... find my one model. Ah, this one. All right, so the first geometry that we are to consider is the V-shaped. Oops, put it in the wrong place now. The V-shaped molecule, okay? What is a V-shaped molecule and how in the world do we need to draw it, okay? Well, a V-shaped molecule, as the name suggests, is going to ultimately look like this, okay? I got these little ball and stick models that I'm going to use a lot in these videos to kind of show you what these molecules look like, okay? But let's say, well, V-shape, why is it V-shape? Let me turn it upside down. It looks like a V, right? Now, what characterizes this V-shape? You see, it looks like a V, but all of the atoms are all existing in the same plane, right? I can put a flat surface. In fact, let me use my top of my model box, and you can see that all the atoms are in the same plane. All three atoms are in the same plane. They just happen to make this V shape when they're bonded together. So how do we draw that? And this is not necessarily, you're not going to be all that surprised by this, perhaps, that perhaps I draw it like this, okay? But what this problem really gets at is an approach that chemists use to tell people the shapes of molecules, or to draw the shapes of molecules. Now this one's not going to be terribly difficult, but other ones are a little bit more complicated. And I want to spend a few minutes explaining this idea to you, okay? So the V-shaped molecule looks like this in the ball and stick model, and I'm going to draw that like that. Now, the important points here are these lines, straight lines, are the bonds that connect the atoms. Of course, you're probably familiar with this by now. But if I just draw a straight line, and I'm drawing a structural representation of the molecule, what that means is that those bonds are in the same plane as the whiteboard or the piece of paper that I'm using to draw my structure on. Okay? So just like all of these atoms are in that same plane, the lines are in that plane as well. The bonds are in that plane, okay? So there's a plane of symmetry, which is essentially the whiteboard, or the piece of paper that I'm working on. That's what those straight lines mean. And it's important to realize that all those are within the same plane. And you may not have heard that before, you may not have realized that, but once you get into organic chemistry, it becomes important to describe the shapes of molecules, how are things arranged, how atoms are arranged around a central atom. So understanding this business is kind of important. So all these are in the same plane. Now, the second example here is what? Trigonal planar. Trigonal planar. Okay, so let me grab another ball and stick here. Okay. So B is trigonal planar. It's another geometry. Now, sometimes people are confused by vocabulary here. Trigonal planar, it sounds kind of complicated, right? What is that? Well, it's not really meant to be all that complicated. What I kind of challenge you to do is just sort of decipher what the words mean. You see trigonal, a triangle, right? And planar, okay? Things are in a plane. So if you look at trigonal planar geometry, it actually looks like this. Notice point A, B, and C, the white spheres, make a triangle, trigonal. And no big surprise, they are what? All the particles are in the same plane. So in this trigonal planar geometry, you see we have a situation where there are what? 3 regions of electron density around the central atom. 1, 2, 3, they're all bonding pairs here. And they form a triangle within a plane. Triangle, plane, trigonal planar. Now, how in the world are we going to draw that? It's pretty simple. We draw our central atom here, denoted A, and then we just arrange a triangle around that. AX3 would be the molecular formula here. Okay? Turns out that the bond angles in a trigonal planar case are 120 degrees. Okay? That's the furthest you can get these bonding pairs away from one another if you've got 3 regions of electron density around the central atom. All right? So that's trigonal planar geometry. Okay, so let's move on. That's A and B. What are the next ones here? Trigonal Bi-Pyramidal. C is something called trigonal Bi-Pyramidal. Trigonal Bi-Pyramidal. All right, now wrap your minds around that for a second. All right, trigonal Bi-Pyramidal. What in the world does that mean? Well, think about it. What do you notice if you see the name, right? You see trigonal for one word. Previously, when we saw trigonal, we thought triangle. Okay, so maybe there's some triangles involved, or a triangle at least, right? We see bi. Well, bi means what? 2, right? So, okay, there's 2 of something. Well, what? 2 of what? Well, pyramids. Pyramidal. 2 pyramids. There's 2 pyramids in a triangle. Trigonal Bi-Pyramidal. So, if we look at a molecular model then of that structure, it would look like this. It's a more complicated structure than what we've dealt with so far. But if you look closely, if you know where to look or how to look, you can find the key structural features. Okay? 1, 2, 3. Those 3 make what? A triangle. Hence the word triangle. And if I rotate that like this, you see I've got one above the plane of the triangle. So the triangle's in this plane right here right now. 1, 2, and there's one in the back. Okay, 1, 2, 3. There's our triangle. I've got a sphere above, or an atom above the triangle, and I've got an atom below the triangle. So if I connect these points, that makes a pyramid on top of that plane. And if I connect the bottom points, 1, 2, with this one, with the one over here, that creates a second pyramid. There's a pyramid above this plane, and there's a pyramid below this plane. So 2 pyramids, bipyramidal, trigonal, 2 pyramids, bipyramidal. They make sense, right? So we get kind of distracted by these fancy names, but ultimately you can kind of reason your way through it, and it makes a lot of sense. But I have a problem. I want to draw this. This is pretty complicated, right? My goodness, how am I going to draw this? Well, usually what I would probably choose to do, or what chemists usually choose to do, is to kind of figure out where a central plane is. Now, the plane that I'm going to choose is right down the middle of the molecule, the axis of these bonds, basically, okay? This one, the central purple, and this bottom one are all going to lie in the same plane in my structural drawing or my representation. Okay, so I'm going to start right there. It's going to be A, and up top is going to be an X, and down bottom is going to be another X. Those are the X's are the white spheres in my model, and the A in the center right here is my purple. So I've got my purple being my A, and then an X and an X on top and bottom. Now notice they're all in the same plane, so I've connected them with single lines. That's going to be the plane of my whiteboard or my piece of paper if I'm writing on a piece of paper. So I've drawn this one, and this one in. But I've got the 3 in the center now that I need to show in my picture, okay? How in the world can I show those in my picture? Because those are much more difficult because they project either in front of the plane or perhaps behind the plane, okay? So how can I draw those? Now, if I arrange this just right, if I tilt it just right, I can also probably put this one in the same plane as this one and this one, okay? It makes a 90-degree angle right here, okay? This one's in the same plane now. So that makes it nice because then I can just do this. Now those are all in the same plane, but I've still got one that projects forward here, and then there's one in the back here that projects back out of that plane. Now these two are not in the plane of the chalkboard, so I wouldn't want to write just a single line and connect them because I'm not really describing the shape. So chemists have come up with another useful way to describe the shape of the molecules. They draw these little wedges into structures, okay? Little wedges, they look kind of like this, okay? the end of my wedge, I'll write an X, which was representative of the atom that's present there. And there's different types of the wedges that you can encounter, okay, in drawings. It's like the one that I just drew here, which is kind of a solid triangular wedge. And this basically has a meaning to a chemist when they see that. If you see a wedge that's a solid wedge, like this one, or this one here, what that basically tells you is that bond is projecting forward out of the plane that it's written in, okay? So remember, I said in my little molecular model here, right, if we look at it, so this one, the one I'm holding, and this one are now all in the same plane, right back here. But this one right here projects forward towards you as you're viewing it. I just drew that one right there. Because it projects forward towards you, I drew it as the solid wedge. But if you look closely, I still got this one in the back that I need to draw here. Now that one is projecting a different direction, okay? I drew the one that projects forward, but this one projects back. Okay, how am I going to draw that? I'm going to draw it with a wedge, but the wedge is going to look different. I'm going to draw a little dashed wedge in this case, okay? So if you see the dashed wedge, that tells you that that bond is projecting back behind the plane of the board. So all this is basically a way to draw on a flat piece of paper and on one plane the shape of a molecule. We use the closed wedges to project forward. We use these wedges to project back. And as a consequence, we're able to draw relatively complicated three-dimensional shapes, using this wedge designation. Okay, so that's kind of the main idea of this problem. And the reason why I wanted to tackle it, so that you could actually see what those wedges were really all about. Now, there's a couple others here, I think, right? Let's see, we had to move on to T-shaped. T-shaped is the next one to consider. It's a little bit of fun to consider these, because you're just learning about these geometries probably, right? We might as well talk a little bit more about them. I don't want to make the videos too long, but we should talk about these guys. What does a T-shaped molecule look like? Okay, well, it looks like this, as the name suggests. Okay, this one's actually a pretty simple geometry. Looks like a T, capital T, if you look at it from that angle. All of the particles lie in the same plane, right? Can you see that? They all lie in the same plane, which makes our life kind of easy, because if I'm going to draw a T-shaped molecule, it's a relatively straightforward one to draw. Just draw it like that. Okay. The bond angles here in a perfect T structure, a perfect T structure, would be 90 degrees. Okay. And of course, this one would be double ladder, 180. Okay. If you're measuring the distance between those two. So this is our T-shaped structure. T-shaped as in Thompson, right? What else we have? Trigonal pyramidal. Trigonal pyramidal, huh? Okay, trigonal pyramidal is one of our base tetrahedral geometries. Let me erase this. On my tetrahedral, I guess. Okay. So the trigonal pyramidal geometry would look like this: central atom in black, 3 other groups bonded to it. Now, if you're going to encounter this structure, there'd actually be a lone pair of electrons right here in your Lewis dot structure. Now, that's not shown because I'm considering molecular geometry here, okay? This is what our trigonal pyramidal structure would look like. Now, why is it called trigonal pyramidal? It makes sense, right? If you arrange them like this, you got a triangle. Like this, you can see that they're not in the same plane, right? Let me get the top of my model kit box. They are not in the same plane. The white ones lie in the same plane, but the black one's up above that, right? See, there's space here. It's up above it. So it's not, a triangle on a plane or trigonal planar. It's trigonal pyramidal. Because if you look like, if you connect the dots, you can make a little pyramid out of it, right? You see that? All right, so how in the world are we going to draw this one? Well, typically what's done is, again, you choose a couple of the atoms, usually as many as possible, to put in the same plane. Now here I think we're going to be able to put 2 atoms in the same plane, the black one and one of the white ones, okay? So if I'm going to draw that, I would have my central atom in the plane of the board, and then I would draw a dash down to an X. Now notice that's a straight line. I did that on purpose, right? To denote that this one and this one are in the same plane. That is, in this case, the plane of the board. This is my A, this is my X. If I move my arm down a little bit, you can see, right? My X and my A, both in the same plane. Now I'm not done yet because I got what? I've got this one in the back, and I've got this one in the front. This one projects forward towards the camera. This one projects back towards the backboard. I need to show that to people, right? So I need to use my wedge perspective. So what I'm going to do to denote my one that's projecting forward, I'm going to do this. My wedge triangle, and I like to shade those in. Okay. That projects forward. And likewise, show one that's projecting back by using my dashed wedge. And I've drawn my trigonal pyramidal structure. Again, on the central atom, I have a lone pair if I encounter that, but this is the shape, this is how chemists would show it, okay? To draw it on a piece of paper to people. You'll see this in, like I said, organic chemistry a lot, so I just want to spend some time on it. It's important to understand these wedge perspective drawings. What else do we have here? We did trigonal pyramidal, so now we have F, which is square pyramidal. Square pyramidal, huh? Okay, let me see. Where's my eraser? Square, one L. Square pyramidal. Now, if you see that name, square pyramidal, what do you start to think about, right? Well, square, okay, I know what a square is. I guess that's pretty straightforward. But what about this pyramid bit? Okay, well, we've already seen pyramids, right? In our Vesper structures, we did that on the last one. So what do we mean by squared pyramid? Well, this is going to be in a base octahedral Vesper geometry, and the structure will ultimately look like this one that I'm showing you right here. Okay, it's going to be a central atom here that's shown in yellow. And you said, well, what about a square? Where's a square? Well, if I arrange it like this, what do you see? 1, 2, 3, 4. If you connect the white dots, you make a square. And sure enough, that square lies in the same plane, so forget about this one for a second. They all lie in the same plane as that yellow atom. So square in the same plane, that's the basis of our square. Now we must have a pyramid somewhere. Sure enough, we do. If I uncover this last one, there's one particle or atom that's outside of that plane. So our plane's down here now. We have one that's above that in this particular case, as I'm showing you, okay? So if we connect those dots, we can also make a pyramid, hence the name square pyramidal. Square pyramidal. Now, how in the world am I going to show this one? Well, again, what I probably try to do, if I can, I guess, is to try to put several of the particles in the same plane. Let's see, what might be easiest to do? It's a little bit hard, but I guess I might try to do something like this, okay? I could do a perspective like this, I suppose, if I really wanted to get fancy. And the reason why I did this, I guess, just to show it in ease of drawing, is to put this top one, the center one, and this one in the same plane. So one, the yellow, and the bottom in the same plane. And if I connect those dots, then I would have something like this. Okay, A, X, X. Single lines denoting they're all in the same plane. But then I've got three more here along the equator, if you will, okay? Or we call them equatorial positions, if you want to think of it like that, okay? One in front, one in back, and then the other one is sort of kind of in the same plane, although it's not true, as it turns out. It kind of actually projects a little bit forward, well, because this is a 90-degree angle, okay? So I could draw something then like solid triangle here, 2x. Solid triangle here, 2x. And I could even, if I want to, in the figure, denote that that's a 90-degree angle. And then I could do wedge back. Okay. And sure enough, if you get the bond angles worked out, it would be a square pyramid. I could also do, if I wanted to draw it a little bit different, just rotate it such that they're all in the same plane. That might also be a little bit easier, okay? But nonetheless, these are our different geometries and drawing them. The key idea from this video, I think, is to understand the sequence, drawing Lewis structures first, okay? We talked about the differences between molecular shape and electron group geometry. That's crucial. And then this idea with the wedges projecting forward or back into the plane, that's also a crucial idea for the video.